Oh, I can't resist a countdown, Mark. Should we pop the first slide up? Okay, we'll start the show. Welcome everybody to the Astronomical Society of Edinburgh. Another one of our fairly intensive series of talks since the lockdown. For anybody who's just joining us, you can find out a lot about the Society, and there's a list of the ways that you can do that. On our website, there are links to all the previous talks, or you can go to the link at the bottom, which will take you straight to the YouTube videos. If you're interested in supporting the Astronomical Society, we're delighted to welcome new members at only £30 a year. Or if you're past your sell-by date like me, or you're in full-time education, it's only 15, and you can do all that online. I think without further ado, I'll ask Mark if you'll introduce tonight's speaker. So over to you, Mark.
Want to do the coming soon first, because that's the next slide.
Sorry. Oh, we usually do it at the end, yes. Coming up soon, on the next two events are next Wednesday, next Friday. We try and do events every Wednesday and Friday. At the moment, we've Clive giving us a talk about circling the moon in 1941, bit of a historical trip back in time. And Horst is going to talk about all my telescopes on Friday the 22nd. Looking forward, we have Dr. Bruce Vickery, who's going to provide us with one or two of his interesting talks. We have a screening of Residence Above the Clouds, which is the video or film made when they recreated some of Piazzi Smythe's trip to Tenerife, along with some students who went back to Tenerife with Andy Lawrence and Brian May. We've got our astroimaging, introduction to astroimaging parts 4 and 5, and part 5 I think Mark might talk about the end of this session. For members, there's a virtual pub quiz coming up in the beginning of June, and a sort of guide to Stellarium, how to find the ASE's 24, the top 24 things you might want to look at. Our imaging group meeting, again, that's members only, another good reason for joining, coming up, the first Wednesday of the next month. And then we're going to talk about Jim on celestial navigation and other things maritime and astronomical, I think. Okay, if that's whetted your appetite, good. Please come again, and I'll hand you over to Mark. Thanks, Mark.
I'm delighted to welcome Dr. Dirk Fruwig from University of Kent to the Society. It's a pity you couldn't make it in person to Edinburgh, but we've got you here virtually, so that's great. I've been speaking to Dirk over the last year and a half since we had a first talk about HOIS, or HOIS CAPS as it was then. Dr. Alex Schultz from University of St Andrews gave us our intro to the HOIS program, and I've been part of that since then, and it's been a great way of being involved in what is really astronomical research. It's quite exciting at times. It was something that I was really needing at the time, because I've done a lot of astro imaging over the years, and then this project came along that allowed me to move it on to the next level and actually using my imaging as part of this project. So it's really quite a good thing to do. But I'll let Dirk introduce the rest of it to you. So I'll just pass over to Dirk. So, thank you.
And while that's happening, I'd just say that if you have any questions, members use the screen share, sorry, the chat at the bottom of the screen. As normal, Peter will pick out those. And if you've got any on YouTube, put them in the comments section and we'll try and do those. Thank you.
Okay, Dirk, over to you. Thank you.
Okay, thank you very much. Thank you for the introduction. this is supposed to be a little follow-up talk from the talk that got previously mentioned by Dr. Alex Scholz. So for those of you who've seen that, the second half will basically be a nice update on what we are doing with the science in the project. For those of you who have not seen Alex's talk, I will give a basic introduction to the project at the beginning as well. So HOIS is basically a project, as Mark mentioned, that is imaging young stars and star forming region. So the talk is mostly about how to form stars, or at least the introductory bit, and planets, and gives a little bit of an overview of which kind of science we actually trying to do. So hence what I'm going to do is basically I'm going to first talk a little bit about star formation in general, how that works, how to make stars and planets as far as we understand it. Then I'm going to explain a little bit why we think we can do this with a citizen science project, i.e. mostly amateur astronomers delivering the actual data, which is the difference to most other citizen science projects that you might have come across, where basically the citizen scientists are involved in the data analysis. Here, we still do most of the data analysis, and we rely on the data from the citizen scientists. And then the second half of the talk, I'm going to basically show you some new results. One from a paper that has been published in January, I think it was, and then something that we're currently working on, which hopefully will be finished. And at the end, if you still are all awake and actually interested in supporting the project, like Mark has done over the past year and a half, I think, and then there are a couple of slides on how to actually participate in the project. What I've been doing together with Alex over the last 2 years or so, we have started to actually advertise the project. The project is older than this, but for about 2 years we have traveled, or I mostly have traveled across the country. So this is the 44th talk about the project. To get to all the other ones, I've driven around 17,000 kilometers to get to you all. The last 2, which were online, involved no traveling, but in total I've spoken now to about 1,500 people. 1 cat, I saw there was another one in one of the living rooms, so I'm going to count that, and also 1 dog. So we got a couple more of presentations that we are going to have over the next couple of weeks. And on the left, this is basically all the other audiences. So if you count them, you should get up to exactly that number of people. But let's start with the actual talk. A little very basic introduction about how stars and planets are forming. So I'm not sure how much Alex has done and how many of you have actually seen that. But star formation basically works in the very basic, like in this cartoon that you might have seen before. Stars or star formation process happens in giant molecular clouds in the interstellar space, which is basically confined to the plane of our galaxy. These clouds, they weigh maybe 1 million to tens of millions of the time of the mass of the sun. So they're extremely massive. They're typically made of molecular hydrogen. There's 1/4 is helium, and 1% of the mass is in dust, so tiny silicate and graphite grains. And it's inside those giant molecular clouds where over time you get regions where the gravitational force is dominating all the other forces that you can get. Because gravity is literally the only thing you need to form stars, because you need to pull that material in those clouds together to make it collapse and form a star. So every now and again, somewhere in those giant molecular clouds, you get regions where gravity is winning over all the other forces that try to disperse the cloud. So these are temperature, so thermal pressure, rotation of the cloud, turbulent motions, magnetic fields, and literally every other thing you can think of will disperse the cloud, gravity will pull it together. And if you get one of those regions where gravity is strongest, the material will basically start to fall to the center, where eventually the star will form. All these clouds, or these parts of the cloud that actually collapse, they all rotate a tiny bit. So what happens in terms of physics is, if material moves towards or inside a rotating system towards the rotational axis, then what happens is that object starts spinning faster and faster. So in terms of physics, that's called angular momentum conservation. If that doesn't tell you a lot, then you might have seen that on TV. If you've been bored enough to watch figure skating, as an example, you see the figure skaters on the ice. They have the arms stretched out and they rotate, and then they pull the arms to their body. So they move some of the mass towards the rotation axis, and suddenly they start spinning faster and faster. And that's the same effect. So that's what happens to these collapsing clouds. And eventually, the rotation speeds up so much that in the equatorial plane of that, you get a very large centrifugal force. And that becomes as strong as gravity and stops the material from falling towards the center in the equatorial plane. Perpendicular to that equatorial plane, there's no centrifugal force, so material can still fall towards the center. So what basically happens is you form very quickly the central object, which will be the star eventually, and you form this disk of material around it, and that's caused by that angular momentum conservation. So to finish the star, basically the material has only the chance to basically fall onto the outside of the disk, be transported through the disk somehow, and then fall from the center or the inner part of the disk onto the star. And this is basically what we are interested in, how that process actually works. Some of the material that falls from the inner edge of the disk onto the star is ejected into these jets and outflows, which I'm not going to talk about in detail, and as I get questions at the end. But eventually that material around where the cloud you started off with, that gets dispersed by either being accreted onto the star, ejected into those outflows, or the star in the middle that lights up, it radiates and pushes away that material as well. So you end up with what we call a classical T-Tauri star, or young stellar object, where you got that forming star in the middle, the accretion disk, and still a jet coming out. And it's the disk we're interested in because this is where the planets are forming. So originally that disk is made up of the same material as your interstellar medium, basically gas and dust. So 1% is made of these tiny interstellar dust grains, silicate, graphite, as I mentioned, and they start basically sticking together and over time form the planets in that system. So eventually, once you get the first planets forming, material can't be transported through the disk anymore because the planet's hindering that. So the accretion will stop. The star is finished, basically. There's no jets coming out anymore. And the rest of the material in that disk is basically converted into the planets. And then you end up with what we call a planetary system. The entire process is very fast. So the initial collapse only takes maybe 500,000 years or so. Astronomically speaking, this is very quick. We also know these disks, they stick around for maybe 1 to 10 million years, which means the actual planet formation process, it's coupled to the star formation process, and it's also very quick. You only have 10 million years basically to finish making all the planets, because we know those disks don't live any longer. So basically, to make planets, you have to stick these 1 micrometer size dust grains together to make something like the Earth or Jupiter in less than 10 million years. So this is basically the bit that we're trying to understand. So one example I have of one of those interstellar clouds is this one, to show you one effect that the dust actually has in those clouds. So I mentioned already, only 1% of the material in terms of its mass is that dust. And if you look at one of those clouds with your naked eye or with a big telescope, then it will look like this. So the cloud here basically is blocking all the light. but it's actually the dust particles in that cloud which scatter and absorb the optical light and basically make all the stars behind that cloud completely invisible. If you go to the infrared, and that's the right-hand side picture, it's exactly the same part of the sky, just that infrared light. Then the absorption, in particular the scattering of the light, becomes less intense. So the blue light is still scattered away from the line of sight, and that's why all the stars that you see look red, because the red light will go through the cloud, and you can see the stars. So in principle, it works like that. We observe a star, and along the line of sight are these interstellar dust grains, and they will scatter mostly the blue light in random directions. The red light is scattered almost nothing. So what you see on Earth with your telescope is mostly the red light from the star. So that's basically exactly the same effect that you see, or one of the reasons why our sky is blue. The blue light is scattered a lot on the atoms, in this case, in the atmosphere, and the red light is coming in a straight line, more or less, to your naked eye. So that's why the blue light seems to be coming from all the directions and make the sky blue. So what we can do is, if you had any idea how the actual light from the star would look like, then you can work out from the color of the star that you can observe how big these dust grains are. Because if you make them larger and larger, let's say you make them from 1 micrometer, where they start off with, to the size of a brick, then they will not scatter the light in this way. They will simply absorb a certain fraction of the light, depending on their size, but that is independent of the wavelengths. So if you had bricks in the clouds, the light of the star would still be dimmer, but it wouldn't change the color. And you can hence use that to basically measure, or at least get a good estimate of the size distribution of the material. So of course, we can't look around the cloud and work out what the actual light of the star looks like. But we're going to come back to this a little bit later in the talk, where we can see that you can actually use this to work out how big are dust grains around these young stars. So as I said, what we're actually interested in is planet formation. In particular, I don't really care personally how things like Jupiter form, because I'm not living on Jupiter. I'm interested in how those terrestrial planets are forming. So things like the Earth. And what we already know is the rocky planets, planets like the Earth, they form very close to the star. So they form within 1, 2, or maybe 3 times the distance between the sun and the Earth, the astronomical unit, from the star. Things like Jupiter, they tend to form further out, roughly where Jupiter is, because this is where all that material in the disk is situated, most of the gas. So hence, if you want to really understand how these planets are forming, we can try to simulate that in a computer. But what we need to know is, how do those accretion disks actually look very close to the host star? So what is their structure? What are their properties very close to the host star? And this is basically one of the things we're trying to do with our project. So let's have a look how these accretion disks look. This is a picture from the Subaru telescope, or 4 of them, of these young accretion disks around forming stars. The stars themselves, they have been blocked out. These are the black circles. This is where the stars will be. And the scale bar here, if you can't read the numbers, it doesn't really matter. They're roughly a couple of 100 astronomical units. So that gives you a typical size of a solar system. And what you see is, with Subaru, which is an 8-meter telescope, probably the best thing we can have, roughly. You see there's a lot of structure in these disks, but what you immediately see is the resolution, the detail you can see, especially very close to the star, it basically doesn't work. You can't, from the ground, with a normal telescope, actually resolve any detailed structure in the inner accretion disk. So Jupiter's orbit would even be very much inside the black circle. So there's no detail on the inner disks. So the outer disks, you can see large-scale structure, and you see there's quite a lot of things going on. So the question is, of course, how can you start resolving the inner parts of those disks? You can throw, as always, money at the problem. You can build the Hubble Space Telescope. That costs you something like $5 billion. You pay another $500 million to repair it. and then it can do things like this. It can image these disks of young stars which are very close. So most of the young stars are in Taurus. There's 3 examples here of these edge-on disks. So disks where you see actually not the face of the disk, you see the edge. So the disk is basically orientated like this. The star is hidden right behind it, so you can't actually see any direct light from the star. What you see as well is the disks are flared. They're not flat like Saturn's rings. They increase in scale height if you go further away. What you see as these white bowls in this example here, where my cursor is basically the scattered light from the central star here that bounces off the surface of that flared disk to the observer. This disk is almost edge on, so both sides look almost identical. And then the green thing here is basically the jet coming out that you can see. There's another example here, an edge on disk. There's no jet in this case. And here as well, the star is hidden here and the disk is blocking all the light. Again, you see these scale bars here, a couple of 200 astronomical units, gives you the right size. But in terms of detail, you can see it's better than what you can do from the ground. But the best detail for the nearest stars you can resolve is 35 astronomical units. You can just about see the orbit of Pluto, sorry, in terms of detail. So this is what $5 billion actually gives you. You can try to spend less money. The Europeans have tried that with ALMA, so radio interferometry in Chile, where you basically put together a bunch of those radio telescopes. And again, you can point them at the nearest star, nearest stars in Taurus, again, something like 300 light years away. And you can start resolving these disks very nicely. You can see the structure in these disks. This is HL tau as an example. So there's gaps, there's rings of material, and so forth. This is radio interferometry. So this is basically not. So all you see here is basically the dust emitting at very long wavelengths. But you get a much better structure resolution. So the detail you can resolve here is about 5 astronomical units. So Jupiter's orbit would be somewhere here. So just in the inner bit, basically. So again, you can actually see now quite a bit more detail, up to 5 astronomical units, but the inner part where the terrestrial planets form, there's no chance even with ALMA. So then the Europeans thought, okay, let's spend even less money, build a very large telescope. That's a bargain, that's 300 million euros or something like that. And then again, you can do this technique where you block the light of the star, and you do this in the near infrared. So this is almost optical light. You can take images, near infrared lights of these nearby disks. And again, they look pretty similar to some of those radio images from ALMA. You see some edge-on objects here. Some really nice ones, which are in Lupus. So this is even closer. The object on the right is PDS 70, where if you're lucky, you find actually a protoplanet in the disk. So this white blob here is actually a planet forming in the disk around that object. There's a second one hidden in this mess up here. But again, this instrument has the same resolution as ALMA, 5 astronomical units for the nearest stars. So if you have stars that are not in Taurus, which are further away, and most things are much further away, then the resolution, of course, is worse. So that doesn't really help you. And it doesn't help you at all to resolve the inner astronomical unit where the terrestrial planets might form. So this is how we think the inner part of an accretion disk will look like. So you got your forming star in the middle, you got the material in the disk around it, and there's structures in the disk which might stick out, either caused by magnetic fields, interactions with planets, and other things. One thing we know is the material in those disks is going to orbit around the central star. So let's say in this case, the material in the front of the star is moving to the right. Now, if some of that material here is moving in front of the star, what will happen is the star will get dimmer. It will also turn redder, because we have these dust particles in here which preferentially scatter and absorb the blue light. Over time, that structure will keep moving, and eventually the star will show up on the other side of that column of material, and the brightness returns to what we used to be seen before the star got kind of hidden by that structure. If there's another structure on either side of that structure, then there will be a second dimming event over time. And if we have some structure here which actually comes back and does the same thing, then we know the orbital period and can work out from the mass of the star how far away from the star it is and how fast this is moving. So what we're doing in our project is essentially we simply measuring the brightness of these stars over time, and we're looking for these dimming events which are caused by structures moving in front of the star and then out again. And from the duration of these dimming events and an estimate of how fast that material is moving, we can work out the physical size of this structure. So basically, if something moves roughly at the speed of the Earth, 30 kilometers per second, and the star is roughly like the sun, then basically any material will take roughly 1 day to move from the left edge of that star to the right edge of that star. So any duration of an eclipse that is 2 days long, we can then simply work out this is twice as big as the star. So that is what we basically trying to do. We're trying to measure the brightness as a function of time and use that to measure sizes. So how much is that actually better than those direct imaging things? So I think Alex probably showed that slide as well. I always use a car because I was driving quite a lot when I gave these talks. I always use a car as an example for the resolution. So your eye is pretty good at resolving things. So your eye can resolve two things on the sky which are 1 arcminute apart. That means it's the same thing as looking at a car that is 5 kilometers away and seeing that there's actually 2 lights instead of 1. So the car lights are about 1.80 meters or so apart. So the best ground-based telescopes, so like Subaru or something like that, they get a resolution of about half an arcsecond. That's all you can do with the atmosphere. And that is equivalent to actually seeing that there's 2 lights on the car if you're about 600 kilometers away. So i.e. For you who are all in Scotland or something near London or something like that, that distance you can actually resolve the 2 lights from the car. The radio interferometry with ALMA and also the BLT with SPHERE, that has a resolution of 0.025 arcseconds. And that corresponds to parking your car about 12,000 kilometers away, basically the other side of the globe. Yes, you need a straight line of sight. And for the nearest young stars, so things in Taurus, which is 300 light years away, that corresponds to the distance between Sun and Jupiter, these 5 astronomical units. Now, our technique basically can resolve, if you observe often enough, our technique can resolve things that has the size of the central star. And the star is typically, let's say, the size of the sun or twice that. And this is about 1 or 2% of the astronomical unit. That is the first improvement we can make. The second one, our technique is independent of how far away these objects actually are, as long as we can see the light. So if the star is further away, as long as we can see it with the telescopes, the resolution still is the same in physical units. So most of the stars in our survey are about 3,000 light years away and not 300, like in Taurus. And if you consider all of that, then we can basically resolve the 2 lights on a car when it is parked on Mars. So that is the improvement. It's about 500 times better than anything you can do with any interferometry techniques. So that is basically the idea, using the timings of occultations to improve or measure very small structures in those disks. And then you can actually also zoom into the star. So the young stars, they still accrete material from the inner edge of the disk. So the material is falling onto the surface, crashes into the surface, and generating shocks and hot spots on the surface. The entire star will also rotate. Some of the young stars, they also have these dark spots like the sun due to the magnetic field. So that entire structure here in the center is basically governed by the magnetic fields. And the surface of the star and the inner edge of the disk, they basically both rotate with the same period. And if you have one large accretion hotspot here, if you can see that, then the star appears brighter. If that spot rotates to the back and you can't see it anymore, the star will get fainter. So basically, what you can also do is you can try to measure and see, is there a periodic modulation of the star? Does the star get brighter or fainter? And does it have hence any of these spots on the surface? And if you actually measure the brightness at several wavelengths in the optical, you can use that, and I can show you some examples later on, to measure not just the period of that star, that is very easy, but also estimate the temperature and the size of these spots on the surface. So that is basically what we are trying to do in this project with the same data. The data is just measuring brightnesses of stars. So it's measuring structures in these disks down to the size of our sun, or 1% of the astronomical unit, and measure temperature, size, and position of these spots on the surface, hot or cold, and the rotation periods. And we're going to do that with telescopes like this. Okay, this is a bit bigger than most of the ones that we have, but a typical amateur telescope, this is the one that we have at the University of Kent. And then we also have some professional telescopes. Some of you might have been there. That is the biggest telescope in the UK that's actually working. And Alex, who gave the talk a year and a half ago, is running this one. So what are we trying to do in detail? Well, we want to do this project long term, so over 25 years to get me to retirement. And we want to basically observe every star in our target list once or twice per day. Twice gets tricky, so you need people in America to help out. But we want to do this in all the possible optical filters, so UV, VRI, and maybe H-alpha. We have about 25 targets. This is not 25 stars. This is star clusters and star-forming regions. So every picture basically contains a couple of hundred young stars. They're all younger than 10 million years, because after that, there's no disks anymore. And they're all within about 3,000 light years, so 1 kiloparsec. That means things like the sun will be a 15th magnitude object. So these small and intermediate sized telescopes can actually see even the low mass stars in those regions. And here are some of the targets. They're selected because they're A, they're star forming regions, but B, because they're very nice and pretty, and everybody takes pictures of it. And we are after those pictures. So everybody has probably taken a picture of the Orion Nebula, maybe the Christmas tree cluster, Pelican, Rosette Nebula, Elephant Trunk. So all these nice things that everybody takes pictures of, we are after those pictures. You can then do whatever you like in terms of making them pretty. We are only after the raw data of these images, including all the old ones that you might have to see what happened in the past. Why do we run that as citizen science? Well, if you have one telescope, then the main problem is when you want to observe, it's cloudy. So this is where our telescope is. This is a randomly selected radar map of the UK. And it typically is cloudy where you are. But it's also, there's a pretty high chance, at least even in the UK, that some part of the country is actually clear, in this case, Wales and Cornwall, very strange. But basically, the idea of the project is hence combine all the amateurs that we have in the UK, and each of these markers is a UK Amateur Astronomy Society, and basically get as many people involved in observing the targets, so that basically whenever it's clear in some place, someone will take a picture of that region in all the filters. That is basically the idea that we had at the beginning. This is where we are now. So we have now actually 67 people who deliver data from 11 countries. The maps show you where all the amateurs are. So all the blue circles are amateur observatories that have contributed. I think this is Mark's. The yellow ones are university stuff. So this is Alex's telescope, that is mine. So we have a number of people in the UK. We've got a large number in Spain, some scattered across Europe, a bunch of people in the US, which are very helpful. And then we got some lucky one who has a remote observatory in Chile, which is quite nice. You get pictures every night. So in total, we've now accumulated about 26,000 images. which if you work that out with the exposure time people have used, this is now almost 600 hours of pure integration time on a 1 square meter mirror. So it's actually quite a large number of exposure time. And in total in those pictures, we have now measured 120 million brightnesses of stars. This is just a graph that shows you the number of pictures as a function of time, how that has increased. So these dashed lines here is every year, and you can see since the last 2 years now, we've achieved a more or less constant rate of pictures coming in every day. So you can see we also have some pictures from before the project actually started. So this is basically these archive pictures that we are after to see what the stars have done in the past. This is one example of the Christmas tree cluster done by Mark Shelley in Ashford. These are 3 pictures taken every 2 weeks a couple of years ago, and they're simply blinking, and you can see that some stars have changed the brightness. So this one, for example, that disappears completely. There's a couple of other ones. I can put them in circles where with the naked eye you can see them change quite easily. But we're not doing this with the naked eye, of course. We basically measure all the brightnesses of all the stars in every picture we get, put them in a database, and then let the computer analyze all the light curves. So that works actually quite easy. The amateur astronomers, they observe, and then they simply do a simple flat fielding and dark correction, and then simply put stuff on our website and tell us for each picture what target it is for and what instrumentation they've used. And then we simply run astrometry using astrometry.net. You don't have to do that. If you do, we wipe it out, we do it again to basically do things consistently. Then we use the source extractor software to simply measure the brightness of all the stars and then do a little bit of maths to calibrate the brightnesses into a reference system. And that is then basically put straight into a database that everybody can access. Now, one of the problems is everybody has slightly different filters. So over the last year, we have developed a calibration routine which actually searches through the database and finds stars that do not vary. And basically, for those ones, we know how bright they are and what the color should be. So if you get a new picture in, we're using all these stars as a reference and then can basically find out if someone has a slightly different filter and correct these so-called color terms in the photometry. So it sounds like quite a witchcraft, but it actually works. So this is one example of one picture where what we've plotted here is only stars that do not change their brightness. And we've plotted the color of the stars compared to the brightness or the difference in the brightness they have in that picture to the brightness they should have in magnitudes. And what you can see is the blue stars on the left, they're brighter than they should be. The red stars on the right, they are fainter than they should be. And there's also some kind of trend with brightness, which is not that clear. And what we do is we simply fit a function to correct that. And after that, all the non-variable stars nicely line up at no difference as a function of color and brightness. So this is one of the worst examples of someone having a really strange filter. But it basically improves the calibration or the uncertainty of the magnitudes from 18% to 4% in this case. So it makes the light curves much better. This is an example of a very red star. If you don't do that correction, this is how the light curve will look like. It looks extremely scattered. There's large error bars everywhere. But once you run the correction over the photometry, what you see is that this star is actually flat. It doesn't vary at all. And the scatter is maybe 1 or 2% at best. There's still the odd outlier, but this is the same light curve. So all these things have basically been moved down and the light curve has been corrected. So that is basically something that we have developed to make much better use of the data from people who have slightly different filters, like from DSLR cameras and so forth. So all these filters are now actually useful because we can correct all these color terms. So as I promised, I was going to spend the last 20 minutes or so explaining a little bit about some of the science we're doing. And Mark got started by helping us, I think, for this object to some extent. It's called V1419 SIC in the Pelican Nebula. It's a very pretty region. And this star here is the one in question. Looks like all the other ones, but it's actually very interesting. So this is a light curve over 2 years of this star in green, red, and infrared. So the black points are the infrared points over 2 years, taken only with our telescope at the observatory. This is mostly to rub in how many clear nights we actually get in Kent. But it also shows you how much data you get with one telescope, even in a not so good side. And what we've done is, what we realized, that star is quite variable. So it changes by about 2 magnitudes. It seems to go up and down over and over again, if you look very carefully. And then we asked all the amateurs in our project to actually observe this star over 6 weeks in the autumn or late summer and autumn in 2018. And this is the data we got for only those 6 weeks. So there's essentially more data points in this plot over the 6 weeks than we had over the 2 years for that star by just using our own telescope. What you can see, this star here, you see a lot of variations. So in the different filters, they seem to be doing the same thing. That is usually means something either like dust changing, the amount of dust is changing in front of the star, and then all the colors behave in a similar way. It's just the bluer light is dimmed more than the redder light in this case. The very red light, the very blue light, the ultraviolet, does absolutely nothing like this. It varies by about 3 magnitudes, more or less in one night. The ultraviolet, however, traces the mass accretion onto the star itself, and that basically tells you the star is still accreting material. And that accretion is extremely variable over a very short time scale. And the same thing, the red minus H alpha, that's what you can see here. Again, that traces the mass accretion process. And again, that is quite variable as well. So the first thing, what you can do is we can have a look at this kind of variability here that we have now for about 4 years of this star, and construct something that we call a variability fingerprint, which basically gives you an idea. If you go to a certain, well, let's rephrase that. It gives you the probability that if you observe the star twice, a given time apart, let's say 1 day, that's here, in terms of time, you do 2 observations, and this graph basically shows you in terms of color, what's the probability that it will change by a certain amount of of magnitude. So what you see for 1 day, it's mostly yellow around 0, i.e. it doesn't change, right? So if you observe it here 2.5 hours apart, the star will most likely not change. But if you go to larger and larger time gaps, so 10 days here, what you realize is if you observe the star 10 days apart, then it has a probability to kind of vary by up to about plus or minus 1 magnitude, more or less homogeneously distributed. And then if you go to larger time scales, and you're finding that suddenly there's a blob here, and that blob happens to be at about 30 days. So basically, if you observe the star twice with 30 days apart, it's most likely actually not changing its brightness again, despite the fact that if you observed it only 10 days apart, it changed somewhere between plus and minus 1 magnitude. And then that disappears again. So what it basically means is there's some kind of period of about a month or 30 days in that star that we can find. What you also see is if you increase the time gap between the observations up to 1 year, we have now 4 years, that star will actually not break out really of its variability. It will, even if you wait 1,000 days, it will not suddenly change by 2 or 3 magnitudes. The probability for that is very, very small. So that's what most of the young stars actually do. So let's have a look at this periodicity here of 30 days. So we can make these periodograms where we basically plot how likely is it that that has a certain period, and there you see a peak at exactly the 30 days that we have seen before. This is just the light curve. There's not much you can see because there's way too many data points. But on the bottom is one of those phase diagrams, or basically you start plotting the light curve, and every period you start from the beginning. and you just keep plotting the data points every 31.5 days. And if you had an eclipsing binary, all the points would nicely line up. And in this case, it doesn't happen. So at phase 0 or 1, which is the same thing, beginning and the end of the period, the star is bright, but in between, it seems to be dimming, but sometimes only a little bit, sometimes quite a lot. So it's periodic, so the period doesn't change, but the amount of change that you see, that varies every time the material, the star goes into one of those dimming events. So the question is, of course, what causes that? So the first thing you can do is you can check, is it actually material going in front of the star and then coming back and doing the same thing again? To do this, you plot the color, in this case, basically green minus infrared, against the brightness, in this case, the blue. So when the star is bright, all the points are up here, so that's where they are. And then what you see is when the star gets faint, it also turns red. We know this is what dust does, but what kind of dust is it? So if you have that normal interstellar dust that you have in those giant molecular clouds, if it was this material, then the light should dim parallel to either the blue or the yellow kind of lines here, somewhere like there. What we see is that it's not the case. What we have is a much steeper decline. So the object gets dimmer much quicker. So it doesn't change color as significantly. So what it means is basically the dust grains that go in front of the star are bigger than the interstellar dust grains. So if you would make them like bricks, in my example from before, we know the color wouldn't change and the starlight would basically just go up and down. You wouldn't see any color change like that. So they're not, we don't have bricks yet. We still have small dust grains, which still scatter the light as a function of wavelengths, but they're bigger than what they started as, i.e. that 1 micrometer size dust grain. So some material in that disk has started to stick together and make larger things, which eventually will be converted into planets. So one thing we can do with knowing the period, we know the velocity the material is moving in front of the star. And then for every time the material comes along, it will dim the star by a certain amount. And we can convert that into the mass of the material that is actually in that structure which is occulting the star for each of the periods. So basically each of these bars is 1 period. So we have about 45 periods of observations. So this is just some arbitrary number here. It just tells you the mass varies significantly. So sometimes there's a lot, then there's almost nothing there. And you can see that changes from orbit to orbit. So the structure has basically mass moving in and out very, very quickly. And you can convert these numbers into actual physical masses. So one up here is something like 0.03% of the mass of the moon, stretched over basically almost the entire orbit in that disk. So you don't need a lot of mass to make these dimming events. So the question is, of course, how do you get these structures? So there's 2 explanations for that. One looks like this. You have a star, you have the accretion disk, and we're looking somewhere at a shallow angle over the accretion disk. And the inner part, because we know this is at about 0.15 astronomical units from the star, because we know the period and we know the mass. So we know this is 0.15 AU. And something on one side of the disk has warped that disk up. The other side of the accretion disk would basically have a warp down. Basically, if we see the star from this side, if the warp is on this side, we see the star dim. But after half a period, the warp upwards is on the other side, and the warp downwards would be here, and then we see the star directly, and the whole system becomes bright. So these objects are called AA tau, where this warping here is caused by the magnetic field of the star, and this happens when the rotation axis of the star is not the same as the rotation axis of the disk. So basically here the star is wrote, this is the equatorial plane of the star, and that would be the plane of the disk. You can get that, and then the magnetic field of the star would warp the disk upwards. That is one explanation. The problem with this is typically these AA tau objects, they have these warps much closer inwards. So they're about 0.05 astronomical units, or rotation periods of maybe a week or so, maybe 10 days. 30 days is much too far out. So the magnetic fields are not strong enough to actually do this. So that is basically no way of saying this could be one of those magnetic structures in these kind of systems. So you could say, okay, we have another bit of material that's just sitting there and orbiting in the disk as a clump. And it's just coming back, and there's sometimes more, sometimes less material. Again, this doesn't work because if you have material in a disk, let's say you have a spherical blob of material, then the bit that is closer to the star, that will orbit quicker than the bit that is a little bit further out. So if you start with a circle or a circle shaped object and you give it one orbit, that object will be stretched by a factor of 6 after one orbit, and it will basically be gone after 2 orbits. So you need something to hold it together. And we've already established it can't be the magnetic field. So the only other way of doing that is a mass, a significant mass. And you need something like a couple of Jupiter masses to do this. I'm not saying that there's a Jupiter mass planet that is dragging some material around it. What we think this object is something like that. So we have the central star in the middle. You have the large scale accretion disk, like the solar system size. And somewhere in the inner part of that system, there's a planet, Jupiter sized. We don't know how much mass, but that has an inclined orbit to the plane of the disk. You only need a couple of degrees. And you can get that very easily by interactions of planets with each other. There's typically more than one planet forming in those disks. And if you get an inclined orbit, what that planet will do is it will tilt the inner part of the disk into its orbital plane. But the whole thing is still orbiting around the central star. So we are looking from here. That's what the telescope means. And in this situation, that part of the disk will block the light to the star. After half a period, we basically see the object from this side, and we look at the star, and the object is bright. So this is what we think that object is. So we think there's a inclined planet, Jupiter-sized, somewhere in that planetary system, somewhere near that radius. It can be within a range of that number, but we don't see that planet directly, but we think it has caused the warping of the disk. Because magnetic fields can't keep it stable over that long amount of time. So we've published this. These are all the images that have been on the paper. Mark is here. So your society is represented on that. So literally everybody after Bringfrid-Steckleum, so everybody from here all the way to here are amateur astronomers who have helped us in the project. The last couple of people are basically observers from our telescope at the university. Very briefly, I want to show you one other example in the same nebula, similar telephone number, similar looking white dot on a nice red background. So what we started to do is basically look at rotation periods of stars. So I picked this object because I knew it had a rotation period from some trials. And then the first thing is we looked at Gaia. Gaia is brilliant. So you can make Hertzsprung-Russell diagrams quite nicely. They actually look like textbooks. These are all the stars towards the Pelican Nebula, but within 500 parsec. The Pelican Nebula is further away. So you remove all the young stars, and the star we are interested in actually turns out to be not in the Pelican Nebula. It's a foreground star. What we've overplotted here, the blue line, is basically the main sequence, but shifted upwards. Basically by 3/4 of a magnitude, i.e. that could be a binary with 2 equal mass stars. Or these 2 red lines here are different age isochrones. So that one here means the stars would be 20 million years old. So we don't know what that object is. It could be a binary with 2 objects of the same mass, or it could be a young star that is 20 million years old. We don't know. What we have started to do is first get together any kind of photometric data point we have over about 10 years. So from our survey, Assassin, Pan-STARRS, the Palomar Transient Factory, the Zwickey Transient Factory, anything from IAVSO. And you can see there's some long-term trend, about 10%, 15% of variability, maybe periodic every 6 years or so. So the hoist caps or the hoist data is limited to the last 4 years here. What we have done first is we removed these long-term trends and looked for short-term variability. And you do plot a parallelogram, and there you see there's a huge peak at about 0.8 days or 19.75 hours. And if you fold that, you get a nice sine function. So there's a lot of scatter here, which basically looks a bit suspicious because there's more points scattered nicely above the curve, and then there's more points here below. So that seems to indicate that the actual amplitude of the variation actually changes over time. So what that means is if you have spots on the surface of that star, they might change in size or temperature, and that's something that we try to investigate. So what we have basically done is, and only look at the top plot here, is as a function of time, so these are 4 years, so the dotted lines here are every 1st of February. We've measured the amplitudes in magnitudes in the green, the red, and the infrared. And you see at the beginning, it was reasonably high, 5 or 6%, then it dropped, went up again, then it increased significantly to about 10%, went down again, went up again, and so forth. And it's currently, the amplitude is increasing again. So you can nicely map out how the amplitude of the variation changes if you have enough data. And HOIST is the only survey that has that. In particular, we have it for several filters. So that allows us, as I said, we can try to estimate the temperature and the size of these spots. So we found out that the temperature of the star is about 5,000 Kelvin. And what you then can do is you have for each moment in time, you know, the amplitudes in the 3 filters, and you say, okay, if I have a 5,000 Kelvin star, I have a spot temperature of, let's say, 5,600 Kelvin, and it has a size that is, let's say, 20% of the surface area of the star. What deviation will that give me? How big would the amplitudes be if there's a spot like that? And how does that compare to the ones that we measure? So the numbers here tell you how accurate can we predict the amplitudes. So basically here that says we can get this right within 0.02 magnitude. So the best fit for that example would be here. You also see that hotspots, which are very large, don't fit because they basically give you completely wrong amplitudes by 0.2 magnitudes, which is clearly wrong. So basically, you can do this for all the measurements that you have. You find basically what is the best fitting model. And that's what you get. This is for the same time. This is the temperature as a function of time. The error bars are quite large, but you can see it changes. It gets hotter, then mostly stays constant, and then drops again in temperature and goes up again. And this is the size of the spot, which is much better determined. So the error bars here are much smaller. You can see it varies from about 30%, then it drops down to 10%, goes up again, down again, and so forth. So that is basically what we're doing. This is now in a stage where this works completely automatically. The computer will basically be given a star, and it does everything by itself. Because what the next PhD student will do is she will basically analyze all the young stars that we have, several thousand, and then we can basically find out how long do these spots live, how big are they typically, how fast do they change their size or temperature, how does that change with the age of the star, and all these interesting things that we can learn about the evolution. So if that is something you would like to do, then participating is actually easy. I don't need to say a lot because you got Mark in your group who's already participating, but we have a website with all the targets on. You can observe literally anything you like in any filter, any exposure time. You need to do is dark correction and flat fielding, stack the images if you take several in one night, and then you simply upload them to our server. It's a reasonably easy process. There's loads of help videos on YouTube. Once you've uploaded them, there's a bit of processing to do. It's basically just telling us what target it is for, extracting things like the exposure time and the date and time of the data from the FITS header, astrometry and the photometry. And after that, once that is okay, it goes into our server, which everybody can query. So there's a little light curve plot tool. You can put in your coordinates or name of the star, and you can basically analyze your own light curve. You can basically download the data and do your own science. You're very welcome to do that. That's one of the things we're trying to encourage people to do. Do your own investigation. There's thousands of stars that are basically there to be analyzed. And then we write papers. So again, there's just a couple of them here. There's a second page, the one that I've already showed you, and some other ones, plus the ones that we are currently preparing. There's a couple more that will hopefully come out soon. So that's it from me. Here are all the details. Any problems, email me. Don't bother Alex. We have a website, as I said. There's a Facebook group, which is probably the easiest way to ask questions. And we have all these help videos, the talk videos and so forth are on our YouTube channel. So if you start doing some science projects, then there will be more things coming on YouTube. So thank you very much.
Thank you very much, Dirk. If members can unmute from mates, I think we'll appreciate it in the normal way. Thank you very much. It is difficult to get, I know, a bit of feedback in these situations. We can ask questions. Peter will probably ask the members questions then.
Okay, I think we had a few off YouTube. Robert Baker asked, why do you see two discs? And Horst answered it. Do you want to say anything more, Horst?
Well, I was wondering whether the context would get lost. So in the HST images, it looks like a hamburger with two bright half buns and a dark slice in between.
Yes.
So there are two bright bits, but they're not two discs, are they?
Yeah. Sorry, go back quickly. Is it? Oh, this one. Yeah. So the disk is actually the dark bit. So the bright bits is basically, so the disks, as I said, they're flared. So that means their top is like a bowl, the bottom as well. And the light from the star that's actually hidden behind the disk is hitting the surface of the disk and then is scattered towards the observer. So you basically see the surface of the disk in those cases here, the same here. So the mid-plane you can't see because there's no scattered light coming out from the star. And you're seeing basically the surface of these of the disk. The disk gets thinner further out. That's why it's easier to see it further away. So the disk is actually the dark bit. Does it make sense?
Yes.
Yeah.
That does to me, I think. Okay, there was a collection of questions from PT on YouTube, and I'm not sure I fully understand the question. But the first one is, sorry, I do not understand the thing about the micron IR readings, either on the telescopes. Are they correct? Not really sure.
Sorry.
I think he's adding a few other things like that. He was confused by some of the readings when you're saying there were 30-meter telescopes. Are they correct? Of the stars in the literature. I mean, I'm not totally sure what the question is as well. But
no, if PT is still there on YouTube, maybe you could clarify your question a bit more. Thank you. In the meantime, Nigel had a question. Nigel?
Yes, thank you very much for a very interesting talk, Dirk. I just wondered, are there any circumstances in which fails to form a planetary system in the end? And if so, why would that be?
Well, there's basically a lot of things can go wrong. One of the things you need to remember is most stars form in clusters. They don't form in isolation. So most stars form in these massive clusters with thousands of members, something like a rich open cluster, or even globular cluster. So there will be a lot of gravitational interaction between all the young stars in that cluster itself, which in some cases, if you get close encounters, that will basically wipe out those disks. It will definitely truncate them. So basically, if you get something of a solar mass moving past here, even every 100,000 or every million years, then that will basically disturb the material enough that it might get ejected. You will probably always, as soon as you have a disk, you probably form some sort of planet all the time. But again, there's loads of them forming at the same time. They will interact with each other, cause a lot of chaos. Many of them will either get ejected, be thrown into the central star. So they definitely migrate. So most of the planets form at some stage and then they start moving inwards. That's how you get all these hot Jupiters, for example. They didn't form kind of where Mercury is. There's simply not enough material. They've moved inwards. If you had any other planets further in that were already there, if something like Jupiter comes along, they're going to be either ejected from the system, thrown into the star, and so forth. So there's a lot of chaos typically going on. If the star in the center is very massive, O and B type stars, the radiation is probably so strong it's simply evaporating everything around it, and the radiation pressure just pushes everything away. And then after 20 million years, the O-type stars explode as supernova anyway. So you don't got long to actually do anything with the planet that you might be forming. So the very massive stars probably don't have planets. I don't know what the most massive star is where we have found a planet. So there's a lot of things, mostly gravitational interactions. And remember also, most stars are multiples, at least binaries. So you might get either a binary inside the middle, you got one circumbinary disk, then you get two things like that. So two circumstellar disks in a binary. That whole thing might have a circumbinary disk as well, with all sorts of weird interactions, orientations, things like that. So all these multiple systems, it's probably quite hard to get planets. They exist, we know that. There are some planets around binaries. But they're much harder to keep there for a long time. So billions of years will be tricky.
Okay, thank you very much.
Thank you. Mark, were you asking that question about DSLRs on behalf of somebody?
Well, I know a lot of people in the society and other places, amateurs have DSLRs. Are they useful in your project, Dirk? And I think alongside with that, someone's asking what's the smallest telescope that could contribute to HOIS?
Yeah, so I kind of mentioned that. So this was the reason I have these slides in there for the color correction that we've done, because most of that scatter is actually slightly different filters. So any filtered observation, if it is something like green, visual, whatever you want to call it, or from the ultraviolet to the infrared, that is useful. That includes all the DSLR filters. Any standard Johnson, Bessel filters, whatever you have, as long as it is filtered, no unfiltered images, but everything that has some kind of filter put in. So if you take your DSLR 3-color picture apart into the 3 channels, submit them separately, that is perfectly fine. We got a lot of people who do that. And the calibration will basically sort out all the color terms and the color corrections during the calibration. In terms of telescope size, the biggest telescope we have is 2 meters. So that's cheating because that's a professional one. The smallest we have is 5 centimeters in diameter. So I don't know what the typical size is. So something about between 10 and 20 centimeters probably. Some people have 20-inch. That is, of course, welcome. So typically, the smaller telescopes are very useful to actually not saturate the bright stars. So our telescope, 17-inch, we do 2-minute integrations and we add a couple of them up. And that typically saturates everything brighter than 10th magnitude. There's a couple of stars in all these clusters which are brighter, which we don't get with our telescope. So the smaller telescopes will basically we will be able to look at those. because they're interesting. These are the more massive objects. There's not that many around. So in the Rosette Nebula, for example, there's a couple of B stars, which typically saturate in the kind of 15 to 20 inch telescope category. But if you have a 5-inch, you'll be fine. So because if you have a 20 inch telescope, there's not much. Eventually, you will saturate things like 7 or 8 magnitude, even with 0 exposure time. They're just too big. So that's what the small telescopes are actually useful for. The only thing I would have to say is in terms of pixel scale, if your pixels are much bigger than 2 or 3 arcseconds, it will get tricky because the stars tend to merge. Many of those clusters are on the galactic plane, and then the photometric calibration is a bit tricky. But then if you pick regions which don't have a lot of stars, then that works quite well, even if your pixels are larger. So avoid things like the Cocoon Nebula. If you got 5 arcsecond pixels, it's not going to work. Basically, all the stars merge into each other, and we can't calibrate it.
Okay. Graham was asking about luminosity from the jets and whether that changes as well.
I spent 10 years of my life trying to understand these jets. I've given up. But what we do know, one of the few things is, so the mass accretion onto the central star, once the disk has formed, happens from the inner edge of the disk onto the star, while at the same time, I can actually go back 1 slide or 2. Yeah. So the accretion happens basically from the inner edge of the disk onto the star along magnetic field lines. And about 10% of the mass that gets kind of accreted onto the star is actually ejected into those jets. So the jets are quite useful to work out how much mass is falling onto the star over time, because they give you basically a history of the mass accretion rate. So the further you go out, the further back in history that material has been ejected. So they move at about 200 kilometers a second. So very quickly they get far enough away that you can see them. And they're typically maybe 0.1 parsec to up to a parsec in length. So they give you a nice history of the mass accretion. Of course, you only see them when they hit something else, which makes the whole thing or the interpretation of that quite messy and difficult. And that's why I personally gave up. So basically, if the mass accretion rate increases, there's more material being thrown out of the jet. And there are some nice Hubble observations where you, so if the mass accretion rate increases, the star will also light up. It gets brighter, the disk will light up as well, because there's more light being scattered off it, it's heated and so forth. And then typically with a little time delay, maybe a couple of years, because of the resolution of Hubble, you then see new knots of material along the jet emerging from the star. So because it travels at those 200 kilometers per second, so you need a couple of years to actually be far enough away so you can distinguish it from the light from the central engine. So I'm not sure if that was the question, but that's what I understood it to be.
Well, we have one or two, a couple more possibly before we.
Can I clarify a couple of things then? So the one earlier on from PT was he was surprised at some of the micron readings of the infrared telescopes, and he's wondering how you convert from kilometers a second frequencies to microns in the infrared readings. I think that's what his question is. I don't know if that makes sense to you.
No, still
No,
not.
okay.
Sorry.
How you convert from kilometers per second to micrometers in infrared telescope readings. Does that make sense?
No, I really don't understand the question. I'm really sorry.
Okay, and just
He has come back again, saying he just wants to know if the reported micron readings on the IR telescopes are correct. I'm sorry, I don't understand the question either, but
yeah,
that's
okay.
maybe because I'm thick. But,
The other clarification we had was back on DSLRs. Ian's asking, you can split up the 3 colors from the DSLR images. Is that without a filter in front of the DSLR as well, or just straightforward the Bayer filter?
Well, the DSLR usually has a biofilter in, right?
Yeah.
So yeah, and then so what you do is you get the 3 color channels. You split them up, and that's what we are after.
Yeah. So you don't need another filter in front. That's right. I think that's what the clarification.
No, because if you put a red filter on, basically your green and blue picture is more or less black.
Yeah. Okay. Thank you.
Okay.
So the DSLR is actually great because if you have a CCD, you have to take one picture after the other to get all the 3 colors. The colors is what we're really after. The DSLR pictures are great because they're taken really at the same time.
Okay, so all our DSLR owners in society, you have no excuse, okay?
Get started tonight. The okay, that's all the questions. Maybe PT would send us an email and we'll maybe trying to get an answer.
Yeah, maybe refer to a slide or something because I don't know what.
Okay, over to you, Andrew.
Thank you. Well, again, thank you very much, Derek. If you'd like to make sure that Mark has your address, we have a
Oh, he does.
Oh, right. We have a small speaker's gift which we'd like to send to you.
Mhm.
Don't tell Alex because we only started doing this after Alex gave his talk. But no, thank you very much. I think that was really enjoyable. Very well described. I managed to follow at least 95% of it. And it's great that you can extract so much understanding out the data. That's always the great trick, isn't it? Getting that miles of understanding out of what is small bits of data. It's wonderful. So thank you again on behalf of the society and everybody else. Great, thank you very much.
Yeah, thank you.
Thank you.
Can I just add in that we've been running an introduction to astroimaging course online for the society, and we've done 3 parts so far. We've got the 4th part coming up very shortly, but we're about to add a 5th part in, which is using your imaging skills for projects like HOYS. So if anyone's really wanting to take up with the HOYS project, then we'll be covering that specifically in session 5 of our course. So please join us for that.
You'll have to follow us on the website or Facebook page, and if you're not a member of the society, just to make sure you don't miss it. Or better still, join us. And with that, I'd like to say good night. Thank you very much, everybody.
Thank you.